Hi everyone. So some of you were gone when we started these notes, so here is a video taking you through the entire lecture. I'm going to bounce between slides and the guided notes that hopefully you have. If you don't have these guided notes, please either get a copy from me or print them out on your own. On Canvas, there's this slideshow, and on the second slide, there is this bad boy, the guided notes. All right. So let's start with a little bit of review. Last week, we talked about electronegativity, right? And when you have two atoms, let's say we have a carbon monoxide, right? Carbon monoxide. That's a carbon and an oxygen bonded together. If we look at their electronegativities, which I should pull up, if you look on the back of your notebook, you can find the electronegativities. So carbon has an electronegativity of 2.5, and oxygen has an electronegativity of 3.5. So their difference is 1. And if you have an electronegativity of anything greater than 0.5, greater than 0.5, but less than 1.7, we call that a polar bond, So in the case of carbon and monoxide, with a difference of 1, this would be a polar bond. And that's kind of all we talked about, right? So today we're really going to dive into what that means and the implications of that in the chemistry world. So on your guided notes, the first thing it wants you to define is what a dipole moment is, a dipole moment. So take a second, and I want you guys to write this right here. When atoms share electrons unevenly, they create a dipole moment. So I'll go over here, and let's write that in. Dipole moment, when atoms share electrons unevenly, they create a dipole moment. Perfect. All right, and then let's also fill in our bonds up here, this little section here. So as I said, an ionic bond is an electronegativity difference between two elements that's 1.7 or more. 1.7 or more. A polar bond is from 0.5 to 1.7, and a covalent bond, a truly covalent, perfect sharing bond, is from 0 to 0.5. All right, so we have those. Now let's talk about some examples. So right here it says example of dipole arrows. So when we have these dipoles, when we have this uneven sharing, we can add some notations to this so that we can read it really well. So I want to talk about this guy right here. What is this? This is hydrogen chloride. Very good, hydrogen chloride. So when we're talking about hydrogen chloride, right, we've got a hydrogen bonded to a chlorine. But when we write this bond, we want to add this notation for whether it's polar or not. So let's look at our electronegativity. And you are writing all of this, please. So hydrogen has an electronegativity of 2.1. Chlorine has an electronegativity of 3.0. So we have a difference of 0.9. Perfect. Well, 0.9 means that it is, in fact, a polar bond. So because it's a polar bond, that means that one of these elements is going to hog the electrons more than the other one. And the one that is the one with the higher electronegativity, which in this case is chlorine. Chlorine is like a stronger magnet. It wants electrons more than hydrogen does. So let's add some notation to this. If chlorine is the hog, that means the electrons are closer to chlorine in this bond than they are to hydrogen, which makes it a slightly negative charge, right? If your electrons are closer to you, that makes you slightly negative. And to write that, we just do this weird symbol. It's kind of like an unfinished 8. And then I'm going to write a negative next to it. Well, of course, if chlorine is slightly negative, that means the hydrogen that it's attached to is slightly positive. So I write the symbol again with a plus sign. All right, that's my dipole notation. But you might notice this says example of dipole arrows. So there's one other thing we need to add, and that's an arrow. So we draw this arrow, and we draw it towards the element that has the higher electronegativity, and then we add this little tail here. The way that I remember it is your tail is by your positive end. See that? My positive, where's my little pointer? my positive, nope. Little pointer, where'd you go? Sorry, I clearly don't know how to work my own little contraption here, and that's okay. Right here. So my positive end here is next to the positive ion, the positive element. Perfect. Okay, so that is how we write out dipoles. That's how we show this polar bond, this polarity. All right, let's move on and go to the second problem. The second problem says draw a water molecule Lewis structure. Okay, so let's review Lewis structures. We need, first and foremost, to know how many electrons we need to draw. So we figure out what we have. We're doing H2O, right? So hydrogen has how many valence electrons? 1, and there are 2 of them. So that's 2 electrons. Oxygen has 6 valence electrons. So I need to account for 8 electrons. Now I'm going to draw my skeleton. H2O, oxygen's in the middle, with an H here and an H here, right? Now these hydrogens are already happy. Agreed? 1 bond. They can only bond once. And I've already accounted for 4 electrons. So I need 4 more. Well, the only place they can go is on this oxygen. So here's my Lewis structure. All right? But to make this even more accurate, let's go ahead and add the shape of this guy. So if we look down here at our molecular geometries that we learned last week, we say, okay, this H2O molecule has 2 lone pairs of electrons and 2 bonds. So we go over to the column that says 2 lone pairs right here. So the shape of this guy has to be bent. So let's redraw it, and yes, I want you to redraw it as well. Let's redraw this guy, but more accurately, bent. So I've got my oxygen bonded to my 2 hydrogens. And my lone pairs of electrons are kind of up here like that. That is the most accurate Lewis structure of water. Okay, now let's go ahead and add our dipoles. So which one of these is the most electronegative? That's what we need to find out. So let's do our electronegativity over here. Oxygen has an electronegativity of 3.5. Hydrogen has an electronegativity of, what did we say, 2.1. So my difference is 1.4. That's really high, all right? So I want you to note that. This is a polar bond. It's a very high polar bond. So who wants the electrons more? That's the one with the higher electronegativity. In this case, it's going to be oxygen. So let's go in and add our dipole notation. If oxygen is the electron hog, that means oxygen is going to be slightly negative, which will make these guys slightly positive. Okay? My electrons are closer to oxygen than they are to hydrogen. It's unevenly shared. Now we're going to draw our arrows. Our little plus sign goes by our plus guys at these. Perfect. Okay. Now we're going to add a couple more pieces to this. I don't think this is complicated, but I do want you guys to just have a full understanding. So let's add a little note right down here, okay? When your arrows, when arrows point towards one element, it's constructive. That's the new word that we're learning. It's called constructive, okay? This is a constructive dipole. And what that means is that these guys, these arrows, are both supporting this oxygen. Everything about this molecule is saying, these hydrogens are saying, hey, we know that the oxygen needs these and we're okay with that. We are lifting up this oxygen, okay? So because they're both going in the same direction, we can draw an arrow like this. This is the direction of our polarity, the direction of our uneven sharing, and that right there is called a net dipole. So make sure you have all of this written down. Pause me if you need to. This is called a net dipole, all right? Okay, so with a net dipole, we're like, okay, great. We know that this molecule is polar. Ooh, let's talk about that for a second. In our last discussion, and in our last example too, up here, we were just talking about the polarity within a bond. But the thing is, Polarity can exist in a bond, but it can also exist in an entire molecule. So an entire molecule can be labeled as polar or nonpolar, just like a bond can be labeled as polar or nonpolar. So if we have a net dipole like we do with H2O, that means that this entire molecule of water is polar. Okay? It has a charge on one end and a charge on the other. In this case, it's negative up here and positive down here. All right? Now let's look at another example. I'm going to go back to my slides for just a second because I forget to use those, and those are really handy. Okay, so bonds can be polar, but entire molecules can be polar too. That's what we just talked about. All right? Now, this is the fancy way of saying exactly what I just showed you on your paper, okay? I want you to look at these slides as you're going through and learning all of this, but this is just like the more scientific way of saying, hey, how can we figure out if our molecule is totally polar? And this is the exact same drawing that you guys just made. Because we have a net dipole right here, that means this is a polar molecule. All right, now, not every molecule that has polar bonds is a polar molecule. So we are going to go back and we're going to draw carbon dioxide in that same little section. So hopefully you're like me and you have some space down here. Let's change our color to red, or actually let's do blue. Okay, let's draw out carbon dioxide. So we need the Lewis structure of carbon dioxide. Carbon has 4 valence electrons. Oxygen has 6, and there's 2 of them, which is 12. So I need to account for 16 total electrons. All right, here's my carbon, here's my oxygen. I already have 4 electrons here, so I need 12 more. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. My oxygen's happy, but what about my carbon? Is my carbon happy? It has 2, 4 electrons. It's not happy. So when in doubt, if you have a failed Lewis structure, share more. So that's what we're going to do. We're going to go back over here. We're going to share more. We're going to make a double bond over here and erasing is hard, and a double bond over here. Now everybody's happy. So this is the Lewis structure of carbon dioxide. Now let's look and see if it's the most accurate one with our geometry. With our geometry, we know that there are 0 lone pairs on this carbon, right? There are no extra electrons. So I'm going to go to the 0 lone pairs column right here, and I have 2 bonds. 1, 2 bonds, right? 1, 2 bonds. So this shape is linear. So our drawing is actually perfectly accurate, which is really exciting. Now let's go ahead and talk about whether or not this is a polar bond. All right, so let's look at our electronegativity differences. Carbon has an electronegativity of 2.5. Oxygen is 3.5, the difference of 1. So all that's saying is that this bond right here, these bonds between an oxygen and a carbon, are indeed polar. Perfect. So we know that we're going to draw our little notation and we're going to draw our arrow. But where are we going to draw our arrow pointing to? Who has the higher electronegativity, carbon or oxygen? It's oxygen. Oxygen has the higher electronegativity, so when I draw my arrows, they need to be pointing towards oxygen. Draw my arrows, and now let's add those fun little symbols. This guy is slightly, any idea? Negative, slightly negative, and carbon is slightly positive. Okay, now let's look back up here at this guy right here. When arrows point towards one element, it's constructive. Is this guy constructive? Are my arrows pointing in the same direction? They're not. So let's add a note to that too. When arrows point in opposite directions, this is called equal and opposite. Equal and opposite, which means it is non-polar. Okay, so the takeaway from this is that, hey, we have polar bonds right here, but this entire molecule, it is not polar. This entire molecule is non-polar. versus up here, this molecule was polar. So that's how we can look at these molecules and decide if they're polar or nonpolar. Okay, let's fill in the blanks down here for the last little part of page 1. Even though there may be polar bonds in a molecule, if bond polarities or dipoles are equal and opposite, they will cancel each other out and there will be no net dipole, right? My net dipole was this thing right here. If there's no net dipole, that means you do not have a polar molecule. Hopefully that helps you guys a little bit. All right, let's zoom on to page number 2. So page number 2 starts with this question, polar molecule, and we're gonna add some rules right up here. So I want you guys to write number 1 right up here like I am. So to figure out if a molecule is polar or not, we do have a shortcut, thankfully. You don't have to go through this entire process that you and I just went through on the first page. So let's look at this. The first step you're going to do is ask yourself, is there a polar bond? If the answer is no, it's a nonpolar. It's a nonpolar molecule. Okay, nonpolar molecule. But if your answer is yes, then you go to number 2. And number 2 says, what is the geometry? So it turns out we learned about molecular geometry for a reason, and that's what we're going to highlight today. So now that we have our 2 steps, I want you to add something with me. Over here on symmetrical shapes, I want you to add a little note with me. Okay? This might be the most important note you write all day. If you have a symmetrical shape, they cancel polarity. And I promise this is going to make sense in a minute. They cancel polarity. I'm even going to highlight this. Like, this is so important. All right? So let's do an example together back on our slides. This is the questions that we just wrote down. Okay, here we have our shapes. And now we're going to look at CF4. So I'm going to go over here. You can write this. Honestly, you don't even have to write this. Just watch me do it, okay? I'm going to write my Lewis structure for CF4, and you're just going to have to trust me that this is the Lewis structure, okay? Here's my Lewis structure. Okay, perfect. Here's my Lewis structure. So now I have to say, okay, do I have any bond polarity here? That's my first question. So we need to figure out our polarity. So fluorine has an electronegativity of 4. Carbon has an electronegativity of 2.5, which means I have a difference of 1.5. Yes, these bonds right here are polar. So I go to my second question. My second question is, what is the geometry of this shape, of this molecule? So let's go back up. We'll go back a few slides. Let's go to this guy. My molecule, CF4, had 0 lone pairs, but it had 4 bonds. So who has 0 lone pairs and 4 bonds? Tetrahedral. Okay, remember that, tetrahedral. Now we're going to go back down to our shape thing, okay? All right, tetrahedral, where do you see that? Is it symmetrical or is it non-symmetrical? Tetrahedral is symmetrical. Let's go back to our notes. What did we say about symmetrical shapes? They cancel polarity. Whoa. Okay, so is this molecule CF4 polar? No. This is non-polar. Non-polar. So that's our shortcut. All we have to do is look at the shape. If you have a non-symmetrical shape, then yes, it's polar. Symmetrical shape, non-polar. Easy peasy. Okay, hopefully you guys feel okay about that. If you don't, you can always come ask me, all right? We are going to move down and start talking about attractive forces. I'm going to stop the video here and make a separate video for these forces that we're going to talk about. So if you missed this as well, make sure you check for the next video.